I'm Victor Costa, and I'll present a hardware accelerator for the Shapelet distance computation in the context of time series classification. I'll begin highlighting the importance of the time series classification task, then I'll show how to use the concept of shapelets to approach this task, and then I'll present the scope of the proposed hardware, our design choices, and the obtained results. To understand why we do time series classification, let's first define a time series as a finite sequence of ordered values. This ordering in most of the cases follows the arrow of time, and in these cases a time series is analog to a discrete time signal. The time series classification task requires a dataset in which each of its instances is composed of a time series and of a categorical value, which we call class. This task is approached in two steps. The first step, train, aims to find a map from time series to categorical variables, to classes. Then, after we find this map, we proceed to inference. In inference, we use the map to assign classes to unknown categorical variables. To make these concepts clearer, let's imagine that our time series come from measurements of a sensor in some equipment, and the associated categorical variable tells us if the equipment is working correctly or not. When using time series shapelets, we are under the assumption that the classes may be discriminated using short patterns of the data. The distance, the similarity between shapelets, is considered to be independent of phase, offset, and scale. This means that the short patterns may be found anywhere in the time series, and that addition and multiplication by constants won't affect the similarity measure. A central concept to this topic is the distance from a shapelet to an entire time series. Since the shapelet pattern may appear anywhere in the time series, we must compute the distance from the shapelet to all the shapelets contained in the time series for some length. The distance from the shapelet to the time series is then the lower distance considering all the shapelets in the time series. The shapelet paradigm was proposed by Yi and Kyo in the context of decision tree classifiers. But later, Hughes and others found that we could make this paradigm more powerful if we instead used shapelets to transform data, enabling its use with any desired classifier. Although these are accurate algorithms, they require lots of computations, and their innermost loop computes the distance between shapelets. In the shapelet transform, this happens both through shapelet selection and through the inference phase, where we transform the data. Both of these algorithms are trying to find good quality shapelets. This is, shapelets that are good in discriminating between classes. To find the quality of a shapelet, let's call it pivot shapelet, we must compare this pivot with all the shapelets in all time series in the entire dataset. That's called disorder shapelet target shapelets. So this comparison is what takes lots and lots of computation. Because of the associated computational burden, there is plenty literature trying to speed up shapelet-based techniques. Since we only need the minimum distance from a shapelet to an entire time series, Yi and Kyo propose that we abandon the shapelet distance computation if the current partial distance becomes greater than the current minimum distance, because in this case, that shapelet distance wouldn't ever be considered the minimum one. So we may discard the shapelets and proceed to the next computation. Rectum-Anon extends the early abandon technique by reordering the shapelet values so that larger values are computed first, so we may abandon the distance computation earlier. Nguyen et al. Show that it's also possible to pre-compute statistics of the data, saving it, and then trading time complexity by space complexity. In another proposal, Cheng et al. Combines then a dynamic programming algorithm for the shapelet distance computation with GPUs to accelerate shapelet-based methods, more specifically the shapelet embedding decision trees. So, our hardware was designed to accelerate the most called function of the presented algorithms. This is the shapelet-to-shapelet distance computation. When computing the distance from a shapelet to another to achieve the so-called offset and scale invariability, we must first z-normalize these shapelets and then, only then, compute the Euclidean distance. This step will be repeated lots and lots of times in the entire algorithms, both in training and in inference phases. Now I'll summarize some of our design choices. First of all, since we always be dealing with two shapelets, one target and one pivot, we first load these shapelets into the chip and keep them in register buffers. Then we will proceed computation with parallel floating point processing units. This is every floating point operation, instead of being applied to a single data point of a shapelet at a time, it will be applied to a chunk of the shapelet elements of a time, accelerating computation. Both parallelism level and the maximum shapelet length, this is the length of the register buffers, are completely parameterizable. We also use the early abandon technique explained earlier, but with a difference. Since we use parallel computation, there is not a single partial distance at a time. We will have multiple partial distance at a time that in the end will be summed by an adder tree. But in this scenario, we cannot use the common early abandon. We should compare every partial distance to a current minimum and then take our decision of abandon or not. Since we do it multiple times to avoid a larger area overhead, we use only the exponent of the partial distances in comparison with the exponent of the current minimum distance. In this way, we are making use of the early abandon technique without adding too much hardware, and we will analyze how good this is. In the PINOUT of our top entity, we may see the parameterizable genetics for number of processing units and maximum shapelet length, and we also see the input and output signals. There is only one data bus in the input and one data bus in the output. Also, we input the operation. We'll see in some moments that we have two operational modes. Our control logic diagram shows that at operation 0, the pivot shapelet is loaded into its buffer, then it's processed until it's normalized, and then it's written back to its buffer. Following, at operation 1, the target's time series is loaded to its buffer, processed until a chunk of it is normalized, and instead of going back to the memory, this chunk will be compared to the equivalent chunk of the pivot shapelet that is already normalized in memory, and if this partial distance triggers early abandon, we leave computation. Else, we continue to the next chunk of the target shapelet to normalize. In this way, at the end of the operation, we will have a distance between two shapelets as the output. It's important to remember that once we do operation 0, we will then do operation 1 multiple times for multiple target shapelets. Now we analyze the results we obtained. In this table, we can see the execution time in cycles for a hardware and for a software implementation, where the software implementation uses the ARM v7 instruction set. In this table, we can see that only for the minimum length shapelet, our hardware has a worse performance. In all other cases, its performance is better, and the larger the shapelet size, the larger our speed up compared to software. And when we have shapelets with length 100 or more, we can see speed ups of more than 5 times when compared to the software implementation. When comparing the proposed exponent-only early abandon with the full early abandon technique, we can see that we are able to trigger early abandon in 75% of the cases in which the full early abandon was triggered. And we also may see that the average leaving point, that is the point where the computation is abandoned, is lesser for the exponent-only abandon because we are doing computation in parallel. So we are taking into consideration more points at one time. Since our hardware is parameterizable, we now investigate the synthesis results for a range of values of each parameter. We synthesize through a 980 nanometers technology. Here we see, for example, that when we double the parallelism level of the hardware, the total power is almost doubled. This doesn't happen with the area, but the area is also greatly increased. When the length of the buffer is increased, we will obviously see an increase in power and area measurements, but not as much as when we increase the parallelism level. So we may conclude that a greater parallelism level consumes more resources than a great buffer length. Since the previous two tables did not extract results from NetList annotated simulations, we must not use them as estimates of the actual power. To do this, we provide this table of NetList annotated results for a range of frequencies at 100 MHz, and in the same configuration as the first line of the other tables, we may see that the actual power, the NetList annotated power, is somewhere close to 2/3 of the estimated power in the other tables. We now break the 100 MHz entry from the last table into its components, allowing us to see the proportion of area and power used by each component, by each floating point operator. In this way, we may see, for example, that although the adder tree only occupies a minor area, its dynamic power is enormous. In this way, our future work will focus on the optimization of our adder tree, and we also consider migrating to a fully pipeline design to improve our true output. We are also considering to compute the distance from one shapelet to an entire time series instead of computing the distance between two shapelets. So thank you, and I believe now we are open for questions.